All right, so where did we ended up last time? Oh, we ended up last time talking about dipoles and electric potential energy, right? So remember that if you bring two charges near each other, right, that requires some force for you to oppose. If they're same charges, that requires some force for them to oppose, for you to push these charges close enough together. So that requires some work, and by doing work on the system, you always either add or subtract energy, right? If work is positive, you're adding energy in the system. If work is negative, you're removing work from the system, right? So that's how what we're going to learn about, what we already learned about the potential energy of these electrically, bound charges. Okay. Kind of just quickly went through dipoles because we don't actually do any math on the dipoles. But before we start today, it's actually kind of a cool day. There's another physicist, is actually in my field of physics, in experimental particle physics. She was born today, Gail Hansen. Actually, I had the pleasure of meeting her once at CERN, which is when I was in Switzerland working for a few years. In 2008, and I think she's retired now, but yeah, it was really cool to meet her when she was visiting SLAC while I was living there. Sorry, not SLAC, visiting Switzerland while I was living there. And she actually is a professor at UC Riverside, but I think she's probably retired by this time. But and elementary particle physics is, if you ever want to talk to me about it, I would probably talk your heads off, and then I'll never let you leave. So feel free to come by and talk to me about that. And there's also, well, there was a research opportunity, but I think those two spots are taken up already. But if you're still interested in it, we can still talk about what you can do in the future. Okay. But today we're going to talk about the electric potential. Okay. So this was really confusing to me when I was taking this class. It's like electric potential and electric potential energy are different things, okay? And maybe I was just not a very good student. I wasn't paying like detailed attention. These two things always confuse me, because I think the person who I took general physics 2 from was European. So I think he wrote his U like this, and then his V was like this, and I can't tell the difference between the two. Okay, so I'll try not to do that. What we learned before, right? Electric potential energy is a type of energy, right? Right, energy. Okay, so U, oops, I'm doing the same thing, right? Big U with an E under it. Okay. And, for example, if you bring two charges close to each other, right, this will be 1 over 4 pi epsilon naught. Charge 1, charge 2 divided by the distance between the two charges, right? What we're going to do now, we're going to try to use this potential energy to derive yet another thing called the electric potential, basically removing the energy part, okay? So it's no longer an energy, okay? You may think, why the heck are we doing this now? Okay, going back to electric force and electric field, remember the idea is that if you have just a single charge, right, a positive or a negative, right, you cannot calculate a force, right? A force requires you to have two charges that are some distance apart, and then you can do Coulomb's law to calculate the force between them. If you have a single charge, right, you can calculate this thing called electric field, right? The idea of an electric field, if I was to put a positive charge here, what is the force, right? That's the idea, right? So you can calculate the field even without the second charge, okay? Electric potential is sort of the energy analog of it, where instead of trying to calculate the potential energy of some charge distribution, right? You have a positive charge here, positive charge here. You can calculate what is the potential energy between them by calculating what UE is. I'm not going to repeat that formula, right? Between these two charges, right? But what if this charge is not there, right? You only have a single charge, right? Is there something we can calculate with that? And that's the electric potential energy, right? Right? Sorry, I already said the wrong thing. That's the electric potential without the energy, okay? And it's a very similar formula as the electric force, where you just basically divide, let me just derive it, right? So in this case, with two charges, right? The electric potential, which uses the letter V, I'm going to capitalize it, okay? It's just whatever the electric potential is divided by the test charge that you would have placed there to test out what is the electric potential at that position, okay? So if you solve this equation, right, you're going to see that, well, if you want to calculate the electric potential energy, you just multiply the charge times the electric potential, okay? Right? This is analogous to, remember when we want to calculate the electric force, right? We just take the charge times the electric field, right? It's very similar, okay? Same idea there, okay? And instead of repeating electric potential, electric potential, electric potential over and over and over again, okay, I'm going to use a more used name that you probably recognize. This is going to be a voltage, okay? So whenever I say electric potential, okay, or voltage, I mean it's the same thing, you know, unless I'm saying the wrong thing, okay? The voltage of something. So when an electrician comes into your house and wire up your houses to have, you know, 120 volts, the voltage on that wall is actually electric potential, okay? Not energy, but potential to have energy, okay? All right, and since this is a much more used quantity, it actually has its own unit called volt, okay? And so voltage has units of volt, so hopefully that's not too confusing, right? And it's named after this guy, Alessandro Volta. So I think he's an Italian guy from the 1700s who studied electrochemistry. Basically, you know, like imagine your car battery, he invented that, okay? And you can argue that all the subsequent batteries we're using these days are also one of his invention. Okay, so let's just do a little, so the book does a little stop to think thing. So if you've seen this in the textbook, you probably might have done this problem on this little exercise or not. So let's say, right, you have some potential lines, you know, where A has a potential of negative 100 volts, B has a potential of 0 volts, and C has a potential of 100 volts, okay? If I was to put a positive charge in here, right, so I'm going to set up this problem, okay? Remember, the electric potential energy is the charge times the voltage, okay? Okay. So whenever you see potential by itself, not potential energy, you can replace that word with voltage, okay? Right? If I was to put a positive charge there, right, what would happen to the positive charge? Is it you know, is this going to just stay at rest at B? Is it going to move towards A at a steady speed, move towards A at an increasing speed, or move towards C at a steady or increasing speed? Okay. Let's see if we can figure this out, okay? How many of you guys vote for A, where it's just going to stay there, right? Because it's at 0 volts, therefore it has 0 potential energy. It'll just stay there, right? A couple of you, maybe you want to do some half volts, which is fine, right? What about how many of you think B is going to move towards the left at a steady speed? Right, move towards A. Okay, none of you? How about C? How many of you guys think it's going to accelerate at an increasing speed? So a couple of you back there also, okay? So any of you guys think it's either D or E? Okay, no one? Okay, so the answer is indeed C, okay? This might be kind of confusing. It's like, wait, we just got introduced to this new quantity, right? How do I figure out what's going to happen to a positive charge with that quantity, right? But the way to think about it is that, well, this voltage thing is related to my potential energy, okay? So from this, I can actually, if I know what the charge is, I know the charge is positive. Right? Actually, I should just do it down here, right? If I know that the charge is positive, right, I can take this potential, right, and basically calculate what is the potential energy of this at different points. So this is, let's say, the point A, point B, point C, right? So let's say I have a 1 coulomb charge, right? Right? The potential energy here is actually going to be, well, I set my axis really badly, didn't I? It's going to be a negative potential energy. My A, my B, my C, right? It's going to be negative 100 volt times 1 coulomb, right? And that's going to be just negative 100 joules. Okay, that's where it is at point A. At point B, well, since the potential is 0, 0 times any number times 0 gives you 0. Okay, at point C is 100 volts, and therefore, right, it should be 100 joule. Okay, this is the potential energy graph, right? Now, if you imagine this positive charge here, right, can we figure out which way it's going to roll? It's going to roll to the left, right? And it's rolling downhill, so it's actually have a constant acceleration to it. It's going to increase in speed, okay? That's why it's actually C, okay? All right, does that make sense? Okay. What happens if the charge is an electron instead? It's a negative charge instead. Can we figure out what will happen to it? Is it A, B, C, or D? It's just, anyone want to yell out the answer? Is what? E, right? Because, right, when you have, in all these problems, right, we just think about, oh, we just assume the charge is positive. But if the charge is negative, it just has the exact opposite force. It'll go in the exact opposite direction, right? So in case it's an electron instead, right, it's going to go to the right at increasing speed, right? Okay, great. So what we're going to do is we're going to use this voltage thing to use this voltage thing to use in our conservation energy problems, okay? Instead of writing the electric potential at the final state or the electric potential initially, right, we can actually just use that definition to say, well, instead of writing the electric potential energy, we can just use the voltage instead, okay? It's just another way to do the same problem. And we'll see how this is actually very useful as opposed to calculating this all the time, okay? So let's do an example real quick. Well, maybe not real quick. The picture is down here. Okay, so one of the challenges of sustainable fusion, meaning fusing atoms together in order to produce energy, as the sun does, for us every day, right, is to bring the two nuclei close enough together. Because if you have let's say a hydrogen atom and another hydrogen atom, the nucleus themselves, they're both positively charged, right? So you have to bring them close enough together so that they can actually fuse together, right? So that's very hard to do. And typically on Earth, what we do is we actually fuse deuterium together, okay? Deuterium, the nuclei is 1 proton and 1 neutron instead, okay? And then so the other one is going to be 1 proton, 1 neutron. When you bring these two guys close enough together, they fuse and form a helium, which is 2 proton and 2 neutrons. Okay, this turns into helium. This is the deuterium, right, both of these, okay? So we're thinking, well, that's a pretty simple process, right? You just bring those two nuclei together, right? But the problem is that both of these nuclei are positive charge, right? So you have to force them together in order for them to fuse together, okay? So the mass of a proton and neutron, we're just going to use the same number. They're pretty close together. It's 1.67 times 10 to the 27 kilogram, and it has some charge of, well, has the elementary charge is 1.6 times 10 to the negative 19 coulomb. Okay, so the idea is that we're going to set up some potential difference between these two guys in order to accelerate them together so that they would actually fuse together when they reach within 1.00 times 10 to the negative 15 meters. Okay, so let's set up the problem, right? Let's do the setup, right? We have this deuterium. I'm just going to use the big word D with a plus sign. Okay, what we're going to do, right, is we're going to have another deuterium here, right? And the idea is that we want to bring this close enough together so that they actually are, the nuclei are overlapping each other, so they're actually going to fuse together. Okay, so if we apply conservation of energy, right, so this has some potential, this is at some initial potential, and this is at some final potential. I'm going to put the little hats on top so we don't confuse them with velocity, right, because, you know, they're all V's, right? Okay, so if we apply conservation of energy, right, so the potential here, right, is going to have to be high enough so that it has to be equal to the potential when they get together like this. Okay, let's see, how did I do this? Okay, so the first thing we need to know, right, is the potential energy of two charges that are going to be close together, right? Going back to our potential energy, right, which is just Q1, Q2 divided by R12, right, with no square. So that's the amount of energy between these two charges, okay? So remember that if we want to convert this to voltage, right, all we have to do is divide out one of the charge. So one of the charge gets divided out. So we're just going to have Q. And since Q1 and Q2 are the same charges, right, they're both deuterium, they're both going to be 1.6 times 10 to the negative 19 coulomb. I'm just going to write Q instead, okay? The distance between the two guys, okay? So let's see. And so the initial state, right, the energy initial, right, since we're just starting them with, you know, there could be some, sorry about that. Didn't mean to write U, Q times VI plus kinetic energy is going to equal to the energy final, which is QV final plus some kinetic energy final, right? Okay, oops. Since we don't actually want these deuterium to be moving around, right? So initially the deuterium is not going to be moving, and then by the time you bring it there, right, it's also not going to be moving, right? So both of these are going to be 0, okay? So therefore, all we have to do is calculate this potential difference between the two. And since the charges are the same, they actually cancel out, right? So VF minus V final, oops, VF minus V initial is what we're going to be calling, so I always forget to put the hats, right? That's going to be the change in potential, right? And that's exactly what a potential difference is, okay? Right? That potential difference has to overcome this amount of potential energy, okay? So instead of writing, it's exactly this, sorry, okay? So instead of writing 1 over 4 pi epsilon naught, I'm just going to put K. Remember that big K is just exactly 1 over 4 pi epsilon naught. The charge divided by basically the distance you want to bring these two charges, okay? So that's going to be 8.987 times 10 to the 9, okay? The charge of the proton, or the deuterium, is 1.602 times 10 to the negative 19 coulomb. And the distance you want to bring them is actually 1.0 times 10 to the negative 19 meters, okay? Right? So let's just cancel out some of these zeros, okay? Right? And if we bring this upstairs, right, this will cancel out the negative 10 to be positive 5. Okay, so this is where I need my calculator because I can't multiply these numbers easily. So 8.987 times 1.602 times 10 to the 5, right, total. Okay, so the total potential difference you need to bring these two deuteriums together. I'm not allowed to move right. What's going on here? There it goes. It's 1.44 times 10 to the 6. And remember the units for a potential difference is a volt, right? Just like the ones in the walls here. Okay, about a megavolt, okay? Right, is that a high voltage or a low voltage? It's pretty high, right? Compared to 120, it's a pretty high voltage, right? You may think, well, that's pretty hard to do. But for subatomic particles, they're actually pretty easy. In fact, we do this every day. And in medical physics, so this is, you know, people who come up with creates instruments that, for example, neutron therapy for cancer treatments. Have you ever heard of that on the radio or know someone who had it? Right. The idea is that what they do is they fuse deuterium together to produce neutrons that has a known energy. And you would think that, well, if you're fusing these things together, right, you must be, right, fusion is supposed to produce energy, right? The problem is that this 1.44 megavolts, it requires you more energy to bring them together than what you would get out of the fusion reaction. So this is actually a way to drain energy, right? If you're doing this at a power plant, you'll just be losing money all the time. The reason they make this is actually because the neutrons are actually useful particles that you can actually shoot neutrons into a person who has, you know, some sort of cancer cell. And when the neutron actually stops inside that cancer cells, it actually kind of like, you know, cause it to be unstable, the molecules inside to be unstable, and actually kind of kills that cancer cell. It's just like a little beam of neutrons that can you know, target specific cells. Okay, so it's kind of a neat little thing. Okay, so that's what we use deuterium fusion for right now, but hopefully in the future we can actually use that to produce energy also. Okay, so that's our introduction to this idea of voltage. Any questions specifically to this example or what voltage is about? Or officially it's called electric potential. Okay, without the E. Yeah, Alan? Right, so what they do is they have a little neutron source, which is a little bit bigger than, you know, so it's like a table-sized top size thing. And, you know, they have the patient stand in front of it, and they calibrate that distance so that they can, the neutron will come out at a certain speed or kinetic energy, right? They calibrate it so that, you know, so that it will pass through a certain amount of tissue. As the neutron passes through your tissue, it slows down, because, like, you know, if you, let's say you throw a tennis ball in the air, it slows down because of the air drag, right? So the tissue drag slows down the neutron. You can calibrate it so it actually stops at a certain place in your body, and that actually having extra neutrons around. Neutron is also an unstable baryon. What's the actual word for it? Nucleon. That's what they're called. An unstable nucleon. So actually, the neutron actually, if you just have it out in the open, it actually kind of explodes in about 16 minutes on average. So they use that energy to use that to kill the cancer cell, basically. Okay. Okay. So now let's talk about another specific example of using the potential, which is the equal potential line between parallel plate capacitors, right? We always have this example of these parallel plates, and we're going to use them over and over and over again because it's just such a nice, simple example, right? The nice thing about parallel plate is, what is the electric field between the two plates? I'm sorry? It's a constant. It's nice, right? Because that's an easy thing to calculate, okay? In fact, you can calculate the electric field between two parallel plates. It's just, this is what you're, might cover on the test on Monday, right? Which is the charge density divided by this constant called epsilon naught, right? So if you were to calculate the potential energy from, let's say, a charge that's inside between these two parallel plates, right? The potential energy is the electric potential energy is just the charge of that particular particle times the constant electric field, which you can calculate, right? Times the distance that you have moved that particular object, right? So this distance s, right? Right? The electric potential, well, it's a simpler version of that because you just divide out the charge, right? So the potential or voltage, right, is just the electric field times the distance that you have moved that charge, right? So in this case, right, if you want to calculate the electric potential across this parallel plate, where the distance s is equal to d, right? All you have to do is just take the electric field times the width of this parallel plate, and that actually gives you the voltage across that parallel plate right away, okay? Which is nice, okay? You don't have to do any integration, any fancy algebra, anything like that, okay? So let's just look at what happens between these two parallel plates, okay? Okay, so inside this parallel plate, right, we're going to start using this nomenclature called delta V, right? This is the difference in potential, right? And this letter C, we're going to start calling these things called parallel plates. So we're going to start calling them capacitors. Okay, instead of calling them, okay, capacitors, okay, with the uppercase. Unfortunately, it's also a letter C, which is not the unit for charge, right? It stands for capacitors, okay? So if you map out the potential across this parallel plate / capacitor, right? What you will see is that the potential is going to increase between the negative to the positive plate, right? Because if you imagine you have a positive charge here, right? In order for you to push it towards the right, you have to put energy into, right? Right? Because these positive charges are going to repel the positive charge you put in here, so it's like pushing a rock uphill, right? So that's why, when you plot the potential across a parallel plate capacitor, it goes up, okay? And the total potential difference between the two parallel plate is this delta V, right? Okay. The word when you're talking about this, the way a lot of people say is the voltage difference between the plates, okay? The plates, or across the plates, depending on who's speaking, right? And remember, voltage and potential is a synonym for each other, okay? Okay. Right? Therefore, if you know the potential difference across a capacitor plate, you can calculate the electric field inside very easily because, right, delta V is just the potential difference between the two sides, and we already showed that is actually E times D, right? If you're interested in the electric field, just solve this equation for E, and then you will see that the electric field between the two plates is actually delta V over D, right? So therefore, this is yet another way to find electric field, right? And notice that the unit here is a little bit different from what we're used to when we first got introduced to electric field, right? Electric field is a force divided by a charge, right? Right. Therefore, it has units of newtons per coulomb, right? That's what this units come from, Now we see that, well, electric field can also be found by just taking potential difference, dividing it by a distance, right? Potential difference has the units of volts, right? I'm going to write it out, right? And distance, of course, has units of meters. So newtons per coulomb is the same units as a volt per meter, right? Because they're both, right, quantifying electric fields, right? Okay. So let's see what happens when we put some numbers into this, okay? Let's say we have some capacitor plates, right? There's some negative plate here, some positive plate here, right? So at the negative plate, we're going to define the potential there to be 0, or the voltage there to be 0. It's just a definition. Okay, we can pick one point to be 0. Okay. As we go through, as we travel across the capacitor, what happens is that, remember, the voltage actually increases like this, right? So at this one particular part, right, it has some plane that has a constant potential, right? Because the charge can actually move up and down here and not change the voltage there, right? Because anywhere along this line, we're at half a volt. Anywhere along this line, we're at 1 volt, right? When we reach the other side, we're actually at 1.5 volts, okay? I think this is probably just actually a battery, right? A AA battery or something like that, okay? So another way to picture this is that if you kind of like have like a three-dimensional view of it, right? This is the negative plate. Anywhere on this sheet, this plane, right, it has the same potential on it. So therefore, a charge on there has the same amount of potential energy, right? This will have half a volt. This will 1 volt. This on the other side is 1.5 volts, okay? And these graphs correlate to each other, right, as you plot the potential graph between them, okay? So in real life, we can actually set up 2 of these as a battery, okay? So the way you would actually construct something like this is by hooking it up to, like a AA battery, which is usually 1.5 volts, right? And if you connect the positive terminal to one plate, what happens is that this will create a potential such that it'll set up the amount of charges in here so that you actually have a 1.5 volt potential across these 2 guys, okay? What physically happens when you connect this battery is that electron starts moving from the back end of the battery and start, getting placed into this other conductor here, okay? And since these electrons are here, right, it's going to produce an electric field pointing towards it, right? Remember, negative charge will create electric field that points towards it. This electric field pointing towards it will actually attract positive charge from the top of the battery towards this end. But since these 2 plates are separated by air or vacuum, right, the positive charge cannot jump over, so therefore they're just kind of stuck there, okay? And that's actually what's physically happening. But we're going to talk about this thing called current in like a couple of chapters, and this is where it'll make a lot more sense then, okay? Okay, there's some examples in the book I really suggest you guys go over. And remember, the idea of doing this example is that you try to do the problem yourself, right? And then if you get the right answer, compare to what the book did and see if there's any difference. If you get the wrong answer, it's actually better, and that way you can actually learn from the example, okay? And the idea of this example, I'm not going to go through the entire example, is that let's say you have some positive charge entering between some gap, so somehow they're able to cut the little hole in here, right? Some positive charge that enters in between two capacitor plates, right? And this has some initial velocity, meaning it has some kinetic energy, right? And what you're going to do is you're going to use conservation energy, right? Where the initial energy is going to be converted to potential energy, right? The potential energy is just the charge times the voltage, right? And then it's going to stop there, and what's going to happen is this charge is going to actually stop here momentarily and get pushed back out, okay? So I won't go through the example for you here, but this is sort of a interesting example that I suggest you go over, okay? There's other applications of charges moving around, right? I talked about neutron therapy. There's also proton therapy, where instead of shooting neutrons at you and having it stop in your body, they shoot protons at you. The difference is that proton is a stable nucleon, so it doesn't explode like a neutron does. But what they do is that they shoot protons into you, and the hope is that they target it so that the energy is mostly deposited in maybe heavier tissue. So this is good for if you were have cancer in a region of your body that is denser than other or near the surface. Because what's happening is that when they do proton therapy, the energy is actually deposited in all the tissue before it also. It's not like a neutron where it just sneaks through, but they try to limit the radiation for these proton therapy. Okay. All right. But that's just an example. So let's talk. Sorry, any questions about voltages in parallel plates? Right. It's one of the simple system, right? The neat thing about parallel plate is that you have a constant electric field, right? So things are easy to calculate. Okay. All right. So let's go to the next harder thing to calculate, electric potential of point charges instead. Okay. Remember, point charges has a different potential energy, right? When we have, let's say we have, some charge, right? We want to determine the potential at some point, some far, nearby the charge, right? What we do, right, you have to do is that while you pretend there's a charge here, and you're going to pretend you're going to bring another charge called Q prime from very, very far away, right? Bring it all the way over here at a distance r from the first one, right? Calculate what the potential energy is there, and you divide by the charge, right? And remember the potential energy here from last time, right? Is this 1 over 4 pi epsilon naught q prime divided by r, right? The distance between them. So if you want to figure out the potential, right, all you have to do is divide both sides by q prime, right? And that will convert it to voltage, okay? Okay. So if you divide this equation by q prime, right, then the q prime actually goes away, and therefore the voltage for a point charge, okay, is once again this 1 over 4 pi epsilon naught thing, right? But just the charge of that point charge divided by the distance you are away from it, okay? Right? So you can make a little plot like this, where let's say we have some spherically symmetric system, okay? And we have some positive charge, okay? Right? Let's look at not this middle plot yet, okay? So when you plot this, right, as a function of r, so this voltage as a function of r, right, you're going to have this 1 over r, right? It kind of looks like an exponential decay, but it's not, right, because it's just 1 over r. As distance increases, the potential decreases, right? As you get to 0, it actually goes to infinity, right? Because 1 over 0 is infinity. Okay. The neat thing about this is that now we have these potential at different radii, okay? And the neat thing about it is that if you are a certain distance away from the charge, you will have the same potential. You will be at the same voltage, okay? And this is what this picture is trying to illustrate. So this is just pretend this is like there's a charge in here, and they're just these green metal balls that surrounds this, okay? There's 3 of them. The one inside, right? So we cut out a little bit so that we can actually just see it, right? So this surface here, this little sphere, right? Anywhere a distance away from that sphere, from that center, right? It'll have the same potential. So here, let me draw this, okay? Marker is good, right? So let's say this is the center where the charge is located, my positive charge, right? So anywhere, let's say 20 centimeters from it, right, on this circle, right, the potential at r equals to 20 centimeter, right? That's the same number, okay? And what the book is trying to illustrate is that not only does it go in this plane, but it's also coming out, right? At this point, it's also the same potential, and all the way in this sphere is also the same potential, okay? So, of course, that's hard to draw, right, in 3 dimension, and that's what this little eyeball-looking thing looks like. But when we try to illustrate this, we do this thing called contour map, where, okay, on these little dashed line, it indicates that these contours are equal potential contours. They're also called equal potential lines, okay? So anywhere on this dotted line, sets of lines, this, right, has the same potential. Anywhere along this dotted line has a different potential from this one, but it's the same on this circle, and it's the same on this circle. Does that make sense? Okay. It's okay. You just have to, I think there's a lab on it, so hopefully you guys get to draw these also yourself. Okay. So, so if we were to set up a sphere of charge due to the spherical symmetry, you can actually prove this, okay? Outside the sphere, the potential is also going to be just Q over R, right? Remember when you have a sphere of charge, right? Right? You can just pretend all the charges is at the center, right? You can model it. Oops, okay, I can write. Whoa. Okay, OneNote just crashed. This happened before already. I wonder because I'm using OBS to record. Okay, let's go back here. Right, let's do this a different color since now I get to do the second time. Right, there's a bunch of positive charges here. You can model this as if there's just a single charge at the center. Right? So the potential for a sphere charge is actually the same thing as just a point charge with the same amount of total amount of charge. Okay? So let's do an example here so we can see this, get some numbers into this kind of a spherical shape idea. Right? So actually we should have brought in the Van der Graaf machine. Okay? So Van der Graaf generator is basically the picture here. It basically just allows you to store charges in a little sphere like this. Okay? And let's say this Van der Graaf machine is charged to a potential of negative 30 kilovolts on the surface, and it has a radius of 10 centimeters. Okay? So I'm going to start drawing this in my setup. Okay? So we have some, let's not use green. It's blue. Right? So that's not a really good circle, but hopefully, let's call this RV for Van der Graaf, right? And RV is 10 centimeters or 0.10 meter, okay? And on this surface, it's telling you that it actually has a potential, right? No, don't type. R equals to 0.1 meter, has a potential of negative 30 kilovolts. Okay, so this is actually telling you that the charges that's on the Van der Graaf itself is actually negative. Okay, so when you have a negative voltage, that means you have a negative charge that's producing that voltage. Okay. Okay. So, and the problem is that find how fast an electron is moving when it leaves the spheres and shock your professor hand 5 centimeters away. So let's say I'm going to put my hand kind of close to it. So my terrible drawing of a hand. Right? What happens is that one of these electrons is going to jump off and basically shock me, okay, by just creating a little lightning across the device itself. And the radius where my hand is located, right, RH, instead of 10 centimeters, it's going to be 15 centimeters. So R is actually equal to, I don't need to write that here, RH is 15 centimeters, or another word, 0.15 meters. Okay? And the task is to figure out how fast this electron is moving. So how the heck do I figure that out, right? Okay. So once again, we use conservation of energy, right? That's probably in the concept part, right? Use conservation of energy. Oops, conservation of energy. Okay. And remember, conservation energy is that the initial energy and the final energy is the same as each other as long as there's no, forces that are removing energy from your system. Okay. The initial energy, if the electron is sitting at rest, right, on the dome, right, it's just going to be, well, could be some kinetic energy, and then there could be some potential times the charge of an electron, right? Since the electron is actually not moving on that surface, we can say that the kinetic energy is 0. Okay. The final energy, right, is some kinetic energy because the little electron is coming flying off and hitting me in the hand. Okay. But it also has electric potential energy, or you have to figure out what the electric potential is. Okay. So the key is to find this, to figure out what this kinetic final is. Okay. So the final kinetic energy, if you solve for this part, is just going to be Q times VI minus VF. Okay. Right. Since the charge of an electron is 1.6 times 10 to the negative 19 coulomb, and since the charge is an electron, we have a negative sign. Right. Right. So we have the V initial, right, which is at 10 centimeter. Right. This is V initial. Right. We have that number, but we don't have V final. Okay. Okay. Right. We don't have V final. Okay. How do I calculate V final? Okay. This is the new information from this section where we have to know that, well, the potential for a sphere of charge, right, is 1 over 4 pi epsilon naught. The amount of charge that's creating that potential divided by the distance r, right? So we know this number for V, for r equals to 0.1 meter. Okay. So what we can do is actually substitute this in and solve for Q, right? Because this is actually negative 30 kilovolts. Okay. So we know this number because that's just 0.1, and this number is just K, right? So the amount of charge here, let's see if I can do the algebra in my head, right? It's negative 30 kilovolts divided by K multiplied by R, right? And R is, let's write this out, even though I'm kind of running out of time. R is 0.1, and K is, I'm just going to do 9 times 10 to the 9 to make it quicker. Okay. So where's my calculator? Negative 30 into 3 times 0.1, 9E9. I can type in the E. Okay, so the amount of charge on that sphere is actually negative 3.3 times 10 to the 7 coulomb. So now we have the Q, right? We can actually calculate the voltage at R equals to 0.15 meters, right? Because that's where the hand is. Okay. If you punch this in your calculator and just plug it into your formula, 1 over 4 pi epsilon naught, charge divided by 0.15 meters instead, you're going to find that this is going to be negative 20 kilovolts instead. Okay. So this is actually what V final is. So now we can plug that up here, right? Negative 1.9 times 10 to the negative 19. V final is negative 20 kilovolts, right? So the difference here, right, is actually negative 10 kilovolts, right? Because minus negative 30 plus 20 is negative 10, right? Okay. You multiply these two numbers together, right? You get 1.6. Oops, the negative signs actually cancel out. So that's the 4 times 10 to the negative 15. And since this is a energy, it will have units of joules, right? Okay. And I'm not going to finish this because I'm over time, but then all you have to do after that is that use your usual definition of, kinetic energy, which is 1/2 mv squared, and solve for V, right? Because you know the mass of an electron, right? Okay, so I'm going to wrap up there today. And I'll probably have to go over the last section, which is it's a very conceptual thing tomorrow. But then tomorrow we're going to focus probably 90% of the class on the midterm review, okay?